All right, welcome APChem squad. We are here in our Kinetics part 3 video, and in this video we are going to learn about the relationship between reactant concentration and time for zero order, first order, and the solid second order. We will now use a graphical method to figure out the order of the reaction and the rate constant, unlike what we saw in our previous one where we were looking at the experimental data. And the experimental data is used to create the graph and how the graph will look. So you'll see that relationship and we will understand the concept of half-life. And we are only going to worry about the first order in terms of half-life, where we had talked about the radioactive elements have half-life. So what is going to be important is your skills from your calculus class. I hope you all understand what it means to integrate an equation. It is going to be important to understand how long a reaction must proceed to reach a predetermined concentration. We will use a mathematical equation, which is again given to you on the back of the periodic table. If you do not have the periodic table handy, I would really recommend getting one. These equations will help us figure out the concentration of the reactant or the product at a given time, and it will also help us yield the time required for a given amount of reactant to product. So we are going to see how we're going to solve this next type of problems that you will be able to see in kinetics unit. So integrated rate law for zero order reaction. Zero order reaction, let's say we have a reactant changing into product. We all know from our first video that the rate can be written as change in the concentration of the reactant over time. And if you're going to integrate this equation, you will write it K times concentration of R, where in this case, if you integrate it, rate is equal to K. So what this means in a zero order reaction, the rate is the rate constant. They are the same. What that means is that in a zero order reaction, rate is independent of the concentration of the reactant. Let me repeat. What we are saying in a zero order reaction, that the rate is independent of the concentration of the reactant. Just like how we had talked about in our previous video, that the rate constant is only dependent on the temperature, it is not dependent on the concentrations of the reactants. However, the rate was changing as the concentrations were changing. But if it is a zero order reaction, the rate constant and the rate will be same. As a result, the rate is independent of the concentration of the reactant. Now, if we look at a first order reaction, again, you don't have to be able to derive this. This equation is given to you. Again, A is changing into product, rate is constant change in concentration of reactant over time, which is equal to K times A because it's a first order. We have talked about the unit. The integrated rate law helps us predict the concentration of a reactant remaining after a given time. So what you do is you take a derivative of the equation, you integrate it on both the sides, and you will, if we are looking at that equation, the integrated first law equation is natural log of concentration of the reactant at certain time is equal to this. Now, this equation is given to you on the back of the periodic table. You should be able to understand all the forms of it based on your laws of log that you have learned. But this is how the equation is given to you on the back of the periodic table. It is not given that this is your first order integrated equation, but you should know that this is what the equation is for the first order. You do not have to worry about how you derive this. Hopefully, this made sense from your math class, how this equation over here can be integrated into an equation. Now, the graphical representation is, if you look at the same equation, if I change it into an equation of line y equals mx plus b, and if I plot a graph, natural log of the concentration of the reactant versus type, I'm going to get a equation, a graph like this, What is important that over here for first order, the slope is negative k. So the rate constant is negative. And this is over here just based on the rate, because rate is an exponential decay. So this is just the concentration, the reactant versus time, while over here, this is after we have integrated the equation, this is the natural log of the concentration of A. So I would recommend drawing this. I have a chart later on where you will copy all these things in one place. Right now, just try to make sense how we have rearranged this equation that is given in terms of an equation of a line. And the B-intercept over here is the initial concentration of the reactant. So in a first order reaction, A decays exponentially with time. To verify that a reaction is first order, if you plot a graph of natural log of A versus time, you expect a straight line. The slope of the line is negative k, and the y-intercept is the natural log of your initial concentration. Now, in a first order reaction, if you plot the concentration of your reactant versus time, by looking at the shape of the graph, you can figure out if the value of your rate constant k is going to be small or large. The characteristic shape of the graph is an exponential decay. The larger the rate constant, the faster the decay from the same initial concentration. If we know the K and the initial concentration, how can you determine how much A is left at a? So you are given this reaction is a first order in A, and the rate constant value is given to you. How long will it take for A to decrease from 0.8 to 0.14? So they have given you the rate constant, they have given you the initial concentration, they have given you a concentration at certain time, and they're asking you to solve for T. Now over here, because they've already given you that this is first order with respect to A, as a result, you can write down your rate law equation and you know that it is first order. So you're just going to use your integrated rate law. You're going to plug in the values. Now this is important that you all solve this correctly. Everybody try to use your calculator and see how this equation is manipulated to solve for T. You can use your properties of log and get this, or you can directly plug in the values and then solve for the T. It depends whichever way works for you. But make sure you're using your calculator correctly. Everybody try it yourself and see if you got this answer. And now at this point, you should be able to solve these 4 problems in your packet. So pause the video, take some time, and then take a little break. Now, half-life. What is half-life? It is the time required for the concentration of a reactant to drop 1/2 its initial rate. And if you all can recall from your Chem 1, when we're talking about the half-life, we are talking about a radioactive isotope that is undergoing an alpha, beta, or other type of decay. So it is represented by actually lowercase t half. Again, this equation is given to you on the back of the periodic table. That is this equation. You will use this equation. Half-life is independent of the concentration of your reactant, right? Whether you have 100 gram of radioactive element or you have 1 ton of radioactive element, it is going to decay. If the half-life of uranium is 1.3 billion years, it is going to take that many years to decay by half. You should be able to look at this. We know that half-life is exponential decay. If the graphical data is given to you, you can see based on if this is your 50%, that is when the half is, you can figure out the time. And as a result, you know this is your half-life. This time could be 1 minute. Let's say it is in 1 minute. So the half-life for this substance is 1 minute. Then after another 1 minute, it's going to become half of that. And that procedure is going to keep going. Okay, so you should be able to look at a graph and understand that it is a half-life and figure out the concentrations. Half-life of the reaction is the time taken for the concentration of the reactant to drop 1/2 of the original amount. So if the data is given, you can just look at it and figure out what the half-life is. But let's see how we're going to solve it using a problem. So if this is your equation, we know initial concentration, half of the initial concentration would be concentration at certain time. This is again a first order reaction, so it is the same integrated rate law. If you plug in the values over here, you solve it, and this is the equation you get for half-life. This is given to you on the back of the periodic table. You do not have to worry about how it is derived here. I've just shown you how we get this number 0.693. Now the question is, what is the half-life of dinitrogen pentaoxide if it is decomposed with a rate constant? So you're given the rate constant value, you plug that value in, and you solve for the half-life. Okay, very simple formula, but you will see when you will solve some problems how they are going to. So being able to understand how and when to apply this formula is going to be a tricky part, but we will get there. How do you know decomposition is first order? Because they gave you that the rate constant, this is the unit, right? So based on the unit, remember I told you, you have to know the unit for the rate constant, and the unit of the rate constant changes based on the order of the reaction. As a result, you knew that this was the equation that you are using. Now, your second order integrated, right? So if you have two reactants changing into product, figure out this is your rate law for a second order reaction. You differentiate on both the side, and then you integrated it, and you end up getting this as your integrated second law. We do not have to worry about half-life for the second order, but this is an integrated second order law of equation that is given to you in your book. Basically, this is moved on the other side. So it's 1 over A minus 1 over A0 equals KT. Doesn't matter. You should be able to manipulate the equation either way. Now, so to summarize everything that we have done is, if you are going to plot a graph of, you have to know the shape of the graph. So I would recommend everybody write down zero order, make a chart, zero order, first order, second order. Write down the graph. You should know the shape of the graph. So if you're going to plot the graph of concentration of the reactant versus time, and you will get a negative slope over here, that is your zero order. Now, if you are getting a negative slope, but now the graph is natural log of the concentration of A versus time. And if you're going to have a second order, then the second order is 1 inverse of the concentration of the reactant versus time. And now your rate constant is a positive slope. You need to know these three equations. They're given to you on the back. You need to know the unit of the K, rate constant. Pause the video, write this, and on the next chart, I also have everything over here as to what you're plotting for each of the graph. A lot of time kids ignore what are the variables that are being plotted. So make sure you're looking at the variables, and as a result, making a conclusion if the graph is representing a zero order, first order, or a second order. Solve some problems. Again, you do not have to worry about these two parts for the half-life. In our AP course, we will only see for the. So what did we learn? We learned that the rate, the change in the concentration of substance per unit time. Rate law, which is your equation when you're writing rate is equal to K with concentrations of your reactants, correct? So it is a relationship between the reactant concentration and the reaction rate. Concentration versus time relationship, it is using a mathematical equation to relate time and concentration. So I hope all this is making sense.